Welcome to a fun and exciting, quick and dirty little lesson on the history of the atom. It all starts off with the ancient Greeks, Democritus. Essentially, they pretty much thought there were only four elements. Their periodic table was pretty simple: earth, air, fire, and water. If you take a knife and you cut an apple in half, and then you take that half and cut that in half, and then you keep on cutting everything in half, it's going to get to a point where you just can't cut anymore. And basically what that was, it got to a point that was so small as an atom, sort of this unbreakable part. And they thought they were circles because they looked up in the sky and everything was circles. And for a very, very long time, really up until the Enlightenment, that pretty much is what we thought, for the most part, made up the atom. And of course then you have the Enlightenment, 1600s, you got Galileo and Isaac Newton. They're thinking, well, maybe things aren't that simple. And on top of that, people start doing what everybody likes to do, is they blow stuff up. And as we blow stuff up and we make things smaller and smaller and smaller, we start tearing stuff apart even smaller and smaller to the point where we really can't tear it apart anymore. And we find that as we can't tear these pieces apart anymore, we start putting these little pieces into different groups called elements. And so by the 1800s, there were a handful, maybe about 30 or 40 or so. And John Dalton was an English science teacher, and a lot of this stuff was coming from England. But he said, hey, look, let's just look at this thing called an atomic theory. And he basically said everything's made up of atoms, small, spherical, with, solids that have measurable properties. So what were some of his theories? Well, if we take a look, this is really what started us off on just chemistry. He said all elements are made up of tiny particles called atoms. Great, we got that from the Greeks. All atoms of the same element are identical. So, for instance, all carbon atoms are the same as every other carbon atom. Atoms are different as we go from element to element, which essentially says, like, for instance, a carbon atom is going to be a lot different from a lead atom. And then finally, the big one was law of multiple proportions, which basically said that atoms of different elements atoms of different elements combine to form compounds, and they always have the set ratio. And finally, atoms are indivisible in a chemical process. That is, you really cannot create and destroy atoms. You can transform them, or they can bond with other atoms. It basically explains a chemical reaction. Now, for the 1800s, this is really pretty good. There are a few exceptions. Basically, we now know that, like, for instance, all carbon atoms are not the same. We have a thing called isotopes, but chemically they're the same. They may have a few different masses. We also know, along with this, that we can't split atoms, and that got into what Einstein did. So what would be some notable things that occurred based after Dalton? Well, first of all, of course, you had Michael Faraday doing a lot with electricity. And one of the things Dalton really didn't talk about was getting shocked, the electrical nature of matter. So, of course, we have to somehow incorporate that idea into the atom. Of course, then also in the 1860s, huge, or chemical superhero, was Dmitri Mendeleev. He basically came up with our current model of the periodic table. His big thing that really was amazing that he did was everybody was trying to make a periodic table with the known elements, and then the next day they would discover some new elements, and then, of course, we had to redo the table. He reasoned that perhaps we had not discovered all the elements. He said, let's group these in families where they all have the same properties. That's where we get our columns from. And let's leave some blanks, assuming maybe we haven't found some yet, where they make sense. And where those blanks were, based on the elements around the blanks, he was able to predict properties that had yet to be discovered. So really, it's his table that really took off. But back to the history of the atom. What are some important ones for nuclear? Henri Becquerel in 1896. Pretty simple. This guy pretty much found a rock in his backyard. He put on some photographic film plates as a paperweight, and he took the picture, and he realized that all he could see was the rock, and so somehow this rock exposed the film. So then he decided to do an experiment. Of course, he put it all in a dark drawer, thinking maybe the rock got energy from the sun, but the same thing happened. Little did he know he discovered a uranium ore practically in his backyard, and that was what was exposing the film. And it really was mind-blowing because it was the first time that really we found an energy source that was not traced back to the sun. J.J. Thompson, pretty neat deal what he did. He basically took a lot of charges, put them in a vacuum tube with there's a little bit of gas in the tube. And the interesting thing was that no matter what gas he used, he would get a stream of particles, which we now know are called electrons. And whatever gas he used, they had the same type of properties. And so he said, okay, look, whatever these things are, they must be inherent to every different type of element. So that he's now saying, well, there must be something smaller than these elements. They have to be small, negatively charged, and moving quite fast. And he basically discovered elements, and it was the precursor of the first TV set. So that was pretty cool. Next one, then, just some more chemical superstars. We'll take a look. Rutherford. Famous gold leaf experiment. He basically took a small, heavily positively charged particle, shot it through some very thin gold foil. 99.9% of the time, it went flying through undeflected, without any problems. So only like 0.01% did it bounce back. Now, Thompson, which I forgot to mention, came up with this model of the atom based on his studies with the cathode rays, calling it the Plum pudding model, which said there has to be this big blob of like almost this pudding that's like the positive stuff, and then there are these little raisins in there of negative charge, which were these electrons which you could easily kick out. So Rutherford wanted to try this, and again, this is at Cambridge. He's bombarded, and also Rutherford was from New Zealand. He was married to a very uptight, straight and narrow wife, who he could never do anything wrong around her. But when he got to the lab and was sort of away from her, he would cuss worse than a sailor. And people kind of made fun of him because he really didn't fit in with the highbrow at Cambridge. But he did the famous gold leaf experiment where he shot these little alpha positive heavily charged particles through gold leaf and came up with this idea that 99.9% of the atom is made up of empty space, and that the 0.01% where most of the mass is this heavily positively charged item called the nucleus. Therefore, these electrons, which Thompson found, must be very small, moving very fast, and way on the outside. And that blew the lid off of everything. And people thought he was on drugs. Even he thought he was crazy, but it was proven to be right. In his notes, he said it was as if, and again, right now people are kind of getting ready for World War I and making these huge guns. He said it was as if somebody had shot a giant cannon, I'd put in a piece of tissue paper up to the shell coming out of the cannon, and the shell stopped the paper, turned around, and went back into the cannon. That's kind of what it was like when he saw this experiment. Another chemical superhero, Marie Curie, who really discovered radioactivity through radium. She isolated tons of it. I could go on forever talking about the work that she did, which I won't. She wanted she's first French woman to get a PhD, first one to win a Nobel Prize. Many people wanted to patent her work and sell it because they could use it in hospitals, but she wouldn't do it. When her husband died, she was not well liked by other women because she'd go to these parties in France and say, hey, I got this really cool stuff in this test tube that glows in the dark, and she would get all the other guys there in a closet and show them her test tube. And the other women, for whatever reason, as you can surely imagine, really didn't like that very much. So she was very interesting there. Her daughter also went on to win a Nobel Prize. But she really was the first one to discover radioactivity and to really nail it down. A couple other notables in the history. Again, the gold leaf experiment was classic, and that was pretty much it there. But a couple other ones. Chadwick in the 1930s. So far we've discovered protons, we've discovered electrons. Neutrons are the neutral particle inside the atom, about the size of the proton, but with no charge. And all of these things we're using to probe the atom, and as we study the atom, they all have charges. The neutron doesn't have a charge. How do you figure out it's there if it doesn't have a charge and doesn't respond to a field? Well, Chadwick, to make a long story short, and to give you a very poor analogy, it was really through momentum. Because he said, look, if you're going to, it's like, imagine this. If I take a football and I throw as hard as I can at a big, heavy linebacker or an 8-year-old tiny little kid, when it hits the tiny little kid, he'll probably bounce farther than the big linebacker because the little kid doesn't have as much mass the big linebacker does. Well, they were doing the same thing with the atom, and it should have bounced farther than it did, but it didn't. And Chadwick said, hey, guess what? There must be something else inside there called the neutron, which has a lot of mass, same as a proton almost, but it has no charge. And which he was found to be right. And that actually led to really fission and fusion. And without that, we wouldn't have come up with the atomic bomb. So that's a quick and dirty history of the atom. If you have any questions, let me know. And we could even do some of these experiments. If you bug me enough, I'll even pull out a cathode ray tube and try to shock somebody with it. It's actually kind of cool. I've shocked myself, and I'm still alive. So, hope this helps, and hope you enjoy it. And let's, let me see if I can figure out how to turn this off. Whoa.